Hey everyone, my name's Aaron Langmead, technical artist and evangelist for Epic Games. Today I'm going to take you through one of the most incredible features in Unreal Engine 5, Nanite. A new system that allows for super fast rendering of geometry, allowing artists to create film quality assets for real-time games. In this talk, we'll explain what Nanite actually is and what it's doing. We'll go through how to set Nanite up on your assets, whether they're existing inside a current Unreal project or whether you're building them from scratch. We'll go through workflow changes that are going to come from this new way of building, mainly covering UVs, and baking and remeshing. And then we'll finish up with some extra things that you need to keep in mind or consider when building with Nanite. When we say Nanite, we're actually talking about virtualized geometry. Similarly to virtual texturing, Nanite loads in only the data it needs to render the scene. Nanite can render high fidelity assets quicker than normal mesh rendering and can render hundreds of thousands of instances dynamically. When you create a Nanite mesh in Unreal, it processes the mesh so that it can render it more efficiently. The mesh is broken down into logical, seamless clusters of triangles based on a number of factors, including smoothing groups and UV seams. Cluster LODs are generated at multiple levels of detail, so they can be swapped out or not rendered at all, depending on distance from the camera, visibility, and the camera frustum. This is different from regular LODs, as it's only loading in the sections of the mesh that it needs to render the scene. When these meshes are being rendered, the best clusters are picked based on the screen percentage they take up. Nanite will always try and keep the difference to the source mesh at less than 1 pixel, so the maximum level of required detail is being rendered, but doesn't waste any memory or processing power rendering triangle detail that would never be picked up. This system makes polycount concerns a thing of the past, but it does come with a few caveats that you'll need to keep in mind when creating. Let's start by answering the most important question of all: how do I enable Nanite on one of my projects? And luckily, this is a really easy question to answer because it's a tick box and it's on any mesh that you want Nanite to be enabled for. All we need to do, if we have a mesh that's already been imported in, we can find it from the content browser, or we can double click on it in the static mesh settings on the scene. Search for Nanite and just tick Enable Nanite Support. Then all you need to do is press Apply Changes, and this mesh will then use Nanite. You can also do this as a bulk action if you want to, just by using the property matrix by right-clicking. Go to Asset Actions and bulk edit via property matrix. And if you're importing a mesh for the first time from something like Blender, we can go to Export, FBX, and let's just call this Canyon Rock example. Press Export. And then we just wait for the mesh importer to pop up, or we can do this manually from the content drawer. Tick Build Nanite. We probably want to untick Generate Light Map UVs as well, if we're using a dynamically lit scene. And for our import settings, in this instance, I'm going to use Import Normals, but by default, this will probably be set to Compute Normals. And we don't want compute weighted normals on unless we want this to be automatically generated for us. Then all we have to do is press import, and then depending on the size of the asset, we wait a few seconds. Now that's imported in, you can see that it's building a distance field for this mesh, and that's now completed, and the DDC got updated. And if I open up this mesh and type in Nanite, we can see Enable Nanite Support is ticked and Build Nanite is ticked as well. And the other quick way of just seeing if this mesh is Nanite inside the static mesh editor is just going to Wireframe, and you'll see that nothing renders. So a Nanite mesh won't render into the Wireframe view mode And that's a nice quick way of making sure that this thing is actually Nanite. Now, there are two other settings that come with Nanite as well. We have position precision and proxy triangle percentage. Let's start with the proxy triangle percentage. Now, when you import a Nanite mesh, it does a lot of work in the background that you don't really have to worry about. But one of the things that it does generate is a proxy mesh. And we can see this proxy mesh if we go to Show and Nanite Proxy. This Nanite proxy is a low-res representation of the original mesh, and it's used for a number of different situations, mainly ones where you wouldn't want to use the super high poly geometry of your normal mesh. So the three core use cases of this are complex collision, which again, we definitely don't want to be using complex collision on a 650,000 triangle mesh. So we use the Nanite proxy instead. The other is light mapping. So this mesh will be used instead of the high poly when it comes to light map baking. And then the third is platform support. If you have a game that's going to release onto the PS5 and the Xbox Series X, but it's also going to release onto some platforms that won't be able to support Nanite, like mobile, then you need a fallback. And the default fallback for this will be the proxy mesh. And that way, you can build your games and your environments and your assets once, and then distribute them across multiple platforms. So when you build for PlayStation and Xbox and maybe high-end PC, you can set it to use Nanite, and the Nanite mesh will be used on those platforms. But when you build out to mobile, you'll use the proxy mesh, which is automatically going to get set to LOD 0. Now, if you don't like the results of the proxy triangle percentage, you have got a few options. The first is changing this percentage. So by default, it'll be 0%. That doesn't mean that the mesh will be 0. It just means that it will use the default triangle count, which is set to 2000. And you can see that on the left here under the Nanite settings. By default, any mesh with a proxy triangle percentage set to 0 will be set to 2000 triangles, unless the mesh is already under 2000 triangles, in which case it will just be that number. If we set this number to 1%, then it will be 1% of the original mesh geometry. This model was 647,000 triangles, so it gets set to 6,470. And you can see we're still looking at the Nanite proxy here, so we can see the actual mesh representation of this asset. If we're still not happy with that for the platforms that don't support Nanite, we can still use the regular LOD levels for those platforms. For the completed version of this mesh, if we go to our LOD settings, I have a number of LODs set for this particular asset. LOD 0 is set to 2000 triangles, which we'll be able to set for our complex collision for our Nanite assets. But for any platforms that don't support it, we'll start at LOD 1 or even LOD 2 or 3. LOD 1 is a much higher triangle count, but still is a normal game ready asset. It's 32,000 triangles, and we can see our wireframe here. And if we go to our LOD settings, you can see our reduction settings. We have percent triangles set to 5%. So this is 5% of the original Nanite mesh. And then if we go to LOD 2, we're setting this to 50% of base LOD 1. And if we go to LOD 3, that's set to 50% of base LOD 2. So for this mesh, I'm just using the base LOD tools that exist inside the engine. But you can also import your own LODs to use instead. The last thing you need to change is minimum LOD. You can set this per platform, and for any platform that won't use Nanite, you just want to make sure that's set to use 1 as a minimum. Next, let's talk about position precision. Nanite assets are highly compressed, which means that you can have millions and millions of triangles in your assets without it immediately filling the hard drive of anyone who wants to play your game. Position precision allows you to set the quality of those compression settings, and by default this will just be set to auto. This will automatically pick the best compression setting for your model based on the size and the density of the triangles of your mesh. If you notice any errors or any issues with your asset, you can override this setting just by picking a different precision setting. You can see your default precision on the top left here in the Nanite settings. This is currently set to 1/16, and we can set this higher or lower based on the compression setting that we want. The last thing that you need to keep in mind with a Nanite asset is the materials that you're using on it. Nanite can handle most material setups, but there are a few caveats to that. Your material can't be set to two-sided, and it has to use the opaque blend mode. You can use most of the shading models, but you can't use world position offset or pixel depth offsetting on your asset. The same goes for opacity and opacity masking with different blend modes. For the most part, as long as you're not using any of these settings, your materials will work just fine. If you do put a setting in onto a Nanite mesh that it doesn't support, the Nanite mesh in question will just render black. So it's pretty easy to tell when you've done something on the material that won't be supported. Now we've enabled Nanite, we want to test it. So we want to see what it's actually doing. And we have some really great previewing options and debugging options to let you see what's actually happening under the hood. If we go to our lighting mode and down to visualization, we can see we have Nanite visualization, and we have a load of different preview modes to actually see what's happening. I'm going to focus on just a few of the really important ones. First, triangles. So we can see our triangle count here, and we can see the number of triangles being rendered in our scene. And as we get closer to these meshes, you can see that this triangle count actually gets swapped out with the kind of more higher density triangles until we reach the original source mesh. But what's great about this is that we're only ever using that kind of level of detail on the meshes where it's actually rendered and actually used. So as we zoom out of this and our meshes take up a smaller and smaller screen size, they actually use a lower and lower triangle count. And we can keep zooming and keep zooming, and you can see that those triangles are getting larger and larger. And this is one of the core benefits of Nanite. It's doing all of that lodding and detail modification per mesh, and it's focusing on just the geometry that you can see. Next up is clusters, and this is where the geometry is grouped together into its logical components. And you can see that these clusters again are getting bigger and smaller as we get closer or further away to this geometry. Next up, we have a really useful one, which is overdraw. And overdraw is still something that we need to be considering on meshes. Now this scene is good. One of the issues that you might notice when using Nanite is when you start having very, very dense geometry overlapping on top of other very dense geometry. This is something you want to try and avoid as much as possible, though obviously you will still use some of it. And this is a really useful way of visualizing that information. So to sum up, Nanite can be enabled on any static mesh that doesn't deform. So that means no skeletal meshes, no world position offset in the material, and you can have both Nanite and non-Nanite assets inside the same scene. They will coexist together happily. Nanite allows for a huge amount of polygon geometry, although it doesn't have to have a huge amount of polygon geometry. And it's able to do this because it renders faster, more efficiently, and only the detail that can be seen at the resolution that it needs to be seen at is loaded and shown. One thing you should understand about Nanite that might not be 100% clear is that while you can have millions and millions of triangles, you don't need to. So all of the assets that you've already generated don't have to be redone. You can still enable Nanite for those assets and you'll still get a gain. Now let's talk about the changes to the art production pipeline if we start using this 1 pixel to 1 triangle ratio for geometry. The old production pipeline method was this. We had our low poly mesh, which we unwrapped. We then created a high poly asset to go alongside this, which would contain all of the detail that we'd want for that low poly asset. And then we would bake the high poly information down onto the low poly. From that bake, we would get normal maps, ambient occlusion maps, curvature, thickness, height, and so on. And then we'd be able to use those baked maps to fake a level of detail that wasn't actually there. And we could also then use that information to texture our final asset. And then we have the new pipeline, which has been used in lots of other industries outside games for quite a while. But we have the high poly pipeline, which is where we discard the low poly instead of discarding the high poly. So we might still start off with our low poly mesh, and we'll probably want to unwrap that in advance. But then we turn that low poly mesh into the high density polygon mesh that we'll use in the final asset. With that high poly mesh unwrapped, we can then bake it, but instead of getting the information that we'd normally only get from baking high poly detail onto a low poly detail, like the normal map, we're just getting information about the curvature and the surface of the high poly that we're working with. So in this instance, we might have an ambient occlusion map, we might have a curvature map, we might have a thickness map, but we wouldn't have a normal map because there's no additional information that needs to be baked onto the asset. And then we can use these textures to build our texture pipeline like we would inside Quixel's Mixer or inside something like Substance Painter. But the real benefit of this pipeline is that you're no longer wasting time generating assets that you aren't ever going to actually use. So with our previous pipeline, we were spending a huge amount of time generating this high poly asset that we then only use for a bake and then have to discard. Now we can directly use the high poly asset, and the low poly just becomes the base that we eventually develop into the final asset. One of the harder parts of building game assets at this higher resolution is UV mapping. Normally this isn't a particularly painful process, but when you're working with such high definition meshes, this can become really difficult. Here I have an asset that is 650,000 triangles, and even just previewing what the unwrap on this is going to look like is really difficult. I have to actually zoom in really far just to see what the actual triangles or quads that I'm working with look like. And even if that wasn't a problem, just moving these elements around is really difficult, let alone unwrapping. But there are a few different ways that you can tackle this to make this a bit easier for yourself. I've outlined a few of the unwrapping steps here that you can use to make working with high definition geometry a bit easier. First, we have the pretty standard methodology, which is building a high poly from an unwrapped base mesh. This is exactly what I've done with this particular asset. You can see that it's a reasonably complex shape, but the actual unwrap itself is just based off a cylinder. So here you can see the side paneling and then the top and bottom of each of these cylindrical tops. The really useful thing about doing this is that we can just start off with these simple base shapes, like this one over here, and then we can modify this unwrap however we want. So in this instance, I had these up here, and I scaled this to match the UV size just to give me as much definition as possible. In this instance, I don't really care about the UV space for the top and bottom of this shape because I know that I'm going to be blending out the top and the bottom of this shape with a standardized texture. Once I've got that, I can start adding some extra geometry to this shape. And let's just add some to the top and bottom as well. And then this model is now ready to go into something like ZBrush, or I can start sculpting it inside Blender's sculpting tools to create the shape I'm happy with. And as long as I don't use any tools to destroy the original unwrap, I'll be able to continue using this, and then once I've finished sculpting, I have my UVs already complete. The second option is preserving your subdivisions and just unwrapping on the lowest level. And there's a number of different ways to do this. Inside Blender, you have the option of subdividing your mesh as a modifier, but you can leave this on as a modifier which preserves the original shape. You can use things like crease to create harder or softer edges, or you can bevel the edges as well. In this particular example that I have here, I have a number of different objects and shapes, each with a different subdivision modifier on, so I can control these independently. But the actual unwrap itself is still showing the base subdivision, which is much easier for me to work with, modify, and edit. The benefit to this is that I never actually have to delete this particular subdivision. I can leave this on as a modifier, and then when I export it as FBX, collapse it down to its actual high definition geometry. And we can do the exact same process again in ZBrush. So here I have the Canyon Rock, and it has 7 subdivision levels, so I can go up and down based on what current process I want to be working on. But all I need to do to work on the unwrap of my low poly is export it out, give it a name, UV example, and then I can import this into Blender, go to my UV edits, and start unwrapping this particular shape. So I'll just mark a few seams here. I will select this loop, mark that seam, and let's just let that unwrap. And for this example, I'm just going to leave this like this. And once I'm happy with that, I can go back in, export, overwrite my existing OBJ file, import that back in. And if I apply a texture map to this, you can see that we've got our new UVs on this particular object. And I can still go up to my original subdivision level. The third option is a little bit more work. It involves recreating the object at a lower subdivision level, unwrapping that and reprojecting. In this example, I use polygroups and Z-guides to create a new mesh at a lower subdivision level. I take this lower poly model into Blender for unwrapping. And once that's unwrapped, I can position my islands and create my UV. Once I'm happy with that, I can bring it back into ZBrush again, subdivide that mesh, and then project it onto the original high poly. With just a little bit of tweaking, I'll have an exact copy of that high definition mesh, but now it's unwrapped. The fourth option is by far the easiest, but will give you the least control over your unwrap. You can use the automatic unwrapping processes inside most applications to give you a very quick and easy unwrap. Back with our Canyon Rock, if we go into the UV editing mode of Blender, select all, and then just tell it to Smart UV Project. You'll see it has to think about it for a few seconds, and depending on the size of your model, it might have to think about it for a few minutes, but it will unwrap the object for you. As you can see, the job that it does isn't particularly great. There's a lot of wasted texture space, and a very large number of islands have been generated, which will most likely create seams when the texture is applied to it. There are other tools that have been created that will do a much better job of automatic unwrapping. Houdini is a good example of this, but there's still no substitute for good unwrap work done by an artist. The final step is to not bother with unwrapping at all. As we're using Nanite, we can use meshes with a very high vertex count, and with that comes a huge amount of potential data in the form of vertex colors. In this instance, I'm baking mask data into the geometry and using that to blend between several world space textures. This means that I don't have to unwrap anything. I can bake series of maps into the vertex colors and then use these to create my unique information. It comes with a number of other benefits as well. To demonstrate this, I have this scene here. These 3 assets are using the exact same material, but create different blends based on the vertex colors that are being used. This saves a huge amount of texture memory, as I'm not having to export any additional textures to the base ones that I'm using. I can just create some base material types. So in this instance, I have a metal, a rust, and a painted metal, and then I can blend between them based on the masks that I'm using. In this instance, I've baked ambient occlusion, thickness, and curvature into the R, G and B channels of the vertex colours, and then I'm using this to blend between these three base materials: paint, rust and metal. Once these are in, I can control the density of this paint information and the strength of the paint information, with an additional noise channel to control the random variation. I could also turn this off altogether, leaving me with just two channels, and I can control the strength of the rust build up on that surface. And then once I'm happy with the result, I can apply this exact material to any other mesh in the scene that has those same channels baked into their vertex colours. This allows me to create lots of different material variation using the exact same materials without having to change any of the properties. So to sum up, Nanite is an incredibly powerful new tool, but it does come with some restrictions. Materials for Nanite can't be two-sided, they have to be opaque, and you can't use tools like world position offset or pixel depth offsetting. Nanite rendering currently doesn't support split screen, forward rendering, MSAA, or the stencil buffer. Keep in mind that Nanite, along with Unreal Engine 5, is in early access. That means that it's still in experimental state and is still being worked on. You can expect many improvements to happen with both Nanite and Unreal Engine 5 as it gets closer to full release. Remember, Nanite is super easy to set up, just a tick box and that's it. It will work on any mesh that will support it. It renders quicker and takes up less memory, so if you can use it, do. You can use the Nanite proxy, imported LODs, or UE generated LODs in place of Nanite for non-supporting platforms, so your game will work across any platform that you distribute onto. Nanite compresses geometry, so file sizes won't be massive. 1 million triangles is about 14 meg on disk. And some final art production tips. Keep your geometry combined where possible. This will allow Nanite to reduce the geometry down more efficiently. Always remember to check your smoothing groups. When you're working with really high geometry meshes, it's actually quite difficult to tell whether you have smoothing groups on or off. Just make sure you've got them on, as this will impact Nanite LOD generation. Try to preserve your subdivisions where possible and unwrap early. It will make your life a lot easier. And finally, I'd always recommend to build at the closest resolution the player will be able to see at and no more. While Nanite compression is very good, having extra levels of detail that will never be rendered or loaded will still take up additional memory. And that's everything. Thanks so much for watching. I hope you found this primer on next-gen art production with Nanite useful. You can find out more about Nanite on our docs page, along with all other features new to Unreal Engine 5. If you want to dive into a live example, you can download the Valley of the Ancients demo from the Epic Launcher. And if you have any questions, you can contact me on Twitter @AaronLangmead.